Hello everyone. Today we're going to look at a few more max and min problems. So let's start with number 5. A window consists of a blue semicircular section on top of a clear rectangular section as shown. The blue glass lets through half as much light per unit area as the clear glass. Determine the radius r of the window that emits the most light if the perimeter of the window is k. So here's the window. We have a semicircle on top of a rectangle. I have taken the liberty of drawing in a few important quantities like the radius of the semicircle, the height of the rectangle, and the width of the rectangle. If we were to extend the radius of the semicircle in this direction, that is also r. So that makes this 2r. So first we can start off with a little bit of unit analysis. So we have light per unit area to deal with. So if we have a particular area and we know this lets through twice as much light per unit area as this, we can maybe see if we can maximize the total amount of light making it through the window. So if we go like this, light equals light per area times area. When I multiply this quantity by this quantity, area cancels and I'm left with light. So if I find the area of the rectangle and the area of the semicircle, I'm well on my way to figuring out the total amount of light. So I'll maybe call this variable L. So L will be the amount of light coming through the semicircle. So this is half the amount of light that's coming through the rectangle per unit area. And I'm going to multiply that by the area of a semicircle. Now the area of a semicircle is pi r squared divided by 2 because the area of a regular circle is just pi r squared. Now for the light being admitted through the clear rectangle, I'll call that maybe 2 out of 2. So this is from this information about light per unit area. So the light per unit area admitted by the rectangle is 2 out of 2. So I don't really care what units light are in this example. It might be percentage of photons that pass through. It might be whatever. It doesn't really matter. If we just say that this is 2 out of 2, we could say that that is the most amount of light that would be emitted for glass. And whatever unit that turns out to be, blue glass will be half as much. So the light per unit area for the rectangle, we need to multiply by the area of the rectangle, which is 2RH. So this is the quantity that I need to maximize. I have an equation in terms of R, but I also have an equation in terms of H. So it might be nice if we can maybe get everything in terms of either R or H. So we need more information. And we can use the perimeter maybe to see what we can do about replacing R or H. So the perimeter, this whole length around the window, is K. That's been given to us, that's assigned. And then we just need to add up all the lengths around the outside. So it's going to be pi r, so half a circle. A full circle, right, would be 2 pi r. We can add up these two h's and add up this width of 2r. So 2r plus 2h. This k is going to be a constant. Depends how big the window is going to be, but that's going to be a constant. It would be a little bit tricky to solve for r because I got two of them, so it might be just simplest for me to isolate for h with this equation and then sub it in there. So let's go ahead and isolate for h here. So h is going to be k minus 2 plus pi times r. So I've just kind of factored out an r from pi and 2, and that's going to be divided by 2. So everywhere I see an h in this equation above, I'm going to sub in this expression. So let's do that. L is going to be pi r squared divided by 4 plus r times k minus 2 plus pi r squared. And now we have an equation for L entirely in terms of r, and this k is going to be constant. So if you want to make a bigger window, this will change and it'll let more light in. But we're looking to maximize this given the amount of material that we're using, I suppose. So let's go ahead and take the first derivative of this. We'll set it equal to 0 and see what comes out for r. So L prime will be pi over 2 times r plus k minus 2 times 2 plus pi times r. So I'm going to expand this and see if I can simplify it a little bit. So I'm going to leave this the same, plus k, and I'm going to get negative 4r minus 2 pi r. I'm going to group the pi r terms together. So I'm going to get next negative 3 pi r over 2, subtract 4r plus k. Now I'm going to set the first derivative equal to 0, and that'll give me a critical value for r. So now let's go ahead and isolate for r and see what value we get. So here we go, 3 pi r over 2 plus 4r. And then I'm going to factor out an r over 2 on the right side of this equation. So I'm going to get r over 2 times 3 pi plus 8. And then I would multiply both sides by 2, giving me 2k. So r equals 2k over 3 pi plus 8. So that is the radius of the window that would allow the maximum amount of light to get through. And you should probably check that the second derivative is going to be a negative at this value on this interval to ensure that it is indeed a max. But the other thing we can do is graph this expression in maybe Desmos. Maybe just swap out L for Y, because Desmos doesn't accept an L. And we can swap out an R for an X. So we can graph X versus Y, and it's happy to do a K. You'll be prompted to add a slider, and you should do that, and then maybe check to see what happens when K is equal to 10, for example. So if the perimeter is 10, you could check what the radius will be, subbing a 10 in there, and you can check the maximum produced by Desmos when K is 10. So you'll get something like that, and you should have something like R or X, right, is going to be 1.148. So you can check that fairly easily on your own. Now on to number 6. Boat A is 40 kilometers west of boat B. If boat A sails east at 20 kilometers per hour and boat B, starting at the same time, sails north 10 kilometers per hour, determine the time when the boats are closest together. So if you took physics, you should really like this question. We know that this will be helpful. Traveling at a constant speed, so A is going 20 kph and B is going 10 kph. We need to figure out when the time is going to be when they're closest together. So they start at 40 kilometers apart, and at time 0 they start moving. So we can maybe let these boats move a little bit and see what happens. So A would go there, B would go there after some amount of time. So given this equation, we can figure out how far they traveled in a certain amount of time by isolating this equation for D. So D is going to be Vt. And in the case of A, it's going to be 20 times time. And in the case of B, it's going to be 10 times time. So the distance traveled here by A is going to be 20t. And the distance traveled here by boat B is going to be 10t. Whatever that t turns out to be, right? After an hour, it would be 20 kilometers. After an hour, this would be 10 kilometers, and so on, right? So we need to figure out what the time is. So the thing that we're trying to minimize in this question is the distance between A and B. So let's maybe call that distance S. This is a right angle triangle, so we can come up with an expression for S using, you guessed it, Pythagorean theorem. So we need to come up with a length for this side and a length for this side. Thankfully, it's pretty simple with this side. It's already there. But the length here is going to need a little bit of adjustment. So that would be 40 subtract 20t. So now we can come up with an expression for S using the Pythagorean theorem. So it's going to be the sum of the squares of the legs of the triangle. So one of those legs would be 10t, and the other would be 40 minus 20t, and they're all squared. Now, as we did last class, it's up to you. If you want to do this, you might cause yourself a little bit of work. So you're welcome to square root both sides and then take the derivative of this with the square root in it. However, what I'm going to do, as I did last class, is I'm going to call a new variable capital S. And if I minimize capital S, then little s will also be a minimum. So capital S is going to be this thing, 10, let's maybe expand it, 100t squared plus 1600 minus 1600t plus 400t squared. So let's maybe group like terms here if we can. So we'll end up with 500t squared minus 1600t plus 1600. And now we are trying to minimize this expression, capital S. We have an equation entirely in terms of t, so all we need to do is take the derivative of this with respect to t, and we're good to go. So it's quite a straightforward derivative to take. We do 2 times 500, which will be 1000t minus 1600. Now we can set this to 0 to figure out what a critical value will be. So 0 equals 1000t minus 1600, and we solve for t, we get 1.6 hours. And that should be the time when the distance is a minimum, but we should probably double check that it is indeed a minimum, right? We could probably fool ourselves, and this might actually be a time when they're at the most distance. So it's a good idea to check, do the second derivative and see what it is. So the second derivative would be just 1000. So it's positive. That means this function s is going to be curve up for all possible values of t. So that's great. Because it's curve up for all values of t, that means this critical value is a minimum. And we're done. Now for the last question of the day, number 7. A cable television company is laying cable in an area with underground utilities. 2 subdivisions P and Q are located on opposite sides of Willow Creek, which is 100 meters wide. The company has to connect points P and Q with cable, where Q is on the north bank, 1200 meters east of P. It costs $40 per meter to lay cable underground and $80 per meter to lay cable underwater. Determine the least expensive way to lay the cable. So I'm going to leave this question up for you to do, but I'll give you a few hints. A massive hint here, I've already drawn a diagram for you. This is P. There's a 100 meter wide creek. Q is 1200 meters to the east of P. And this dotted line I've just put in as a potential path for cable. So this section here is underground, and then it's underwater direct to Q. We need to figure out how long this underground section is going to be, right? This value for x that we solve might end up being 0, right? So if you go the full way, maybe there to there, and then cut straight across to Q, that might be a possibility. Probably unlikely because it seems like we're adding a lot of distance, right? The shortest distance between 2 points is a straight line. So if we take this path, that's probably going to add some cost because we're adding cable. And we can't probably very well go from P direct to Q because it's quite expensive, right? So a good way to start this question is again by unit analysis. So I would define cost like this. So dollars per length times length. And then when you multiply this through, length divided by length disappears and you're just left with a number in dollars. So you're going to have to add the cost required to go underground and the cost to go underwater. I will tell you also that whatever value you come up with for the cost should be less than this path. So if you go all the way here underground and then go straight across, what you're going to get with that, so that would be the solution when x equals 0. The cost would be around $56,000. And the other solution, so if x was 12, that would be the direct route, right? Because this x, 1200, that would mean this x takes up this full length. That means we go direct. So if x was 1200, we would get a cost of $96,300. $333. So when you do this question, you need to minimize this. Once you have your pieces, make sure it's all in terms of one variable. So it might be good to express it entirely in terms of x, right? Get rid of the r if you can. You know, this side is 100. This is x, that's r, and you're off to the races. Okay, that's it for today. Take care.